class will be going a lot slower than usual. But also since it's the first week of the semester, I think everyone is still trying to adjust themselves. Because you all have like the 3 months vacation, right? Did you guys get the chance to travel around Taiwan? No? Or just stay within Taipei? I mean, if you get the chance, maybe like there are so many places in Taiwan you can visit. It's like once in a lifetime opportunity. If you leave, it might be a few years before you come back. So if you have a vacation or summer vacation, you can try to go around like southern Taiwan, or you can even go to the other islands. There are so many beautiful places. Especially if you like nature. Taipei can be a little bit too crowded. Yeah. So we will just quickly review like what we did yesterday, and we will continue on from there. Okay, so if along the way there is like anything you don't understand, you can just ask. Yeah, we are not in a hurry. Okay, and I'll also show you some videos with regards to because yesterday we were talking about the soil strength parameters. How do we determine like the strength parameter, that is the friction angle or the on-drain shear strength, right? We talked about using the SPTN, that is the strand penetration test, and also the cone penetration test. So it's like, it's kind of difficult to visualize how the experiment is actually done if you don't really see it. So I'll show you like some videos later that will explain in detail like how they perform the experimentation, okay? So yesterday we basically talked about two major things. We talked about the drain analysis and the on-drain, right? Okay. So for the drain analysis, we say mostly is the coarse grain soils, right? For example, sandy soils. Okay, they will be in the drain condition. And for the on-drain, we talk about the fine grain soils, for example, clay and silt. Okay, and we say the principle here is actually very, very simple. Okay, for the drain analysis, because the particles are not very fine, if you apply loading onto the soil, what happens? The water can easily come out, right? And if you remove the loading, what happens? The water can easily go back in. Okay, it's a pretty simple idea, just like when you go to the beach, because it's mostly sand, very coarse. You step on the sand, what happens? Water comes out. If you remove your feet, what happens? The water just disappears, right? Which is quite different if the soil is clay or silt, right? Water may be inside, but if you step on it, you will not likely see water coming out. Why? Because the space, like the particles are too tiny, so the water cannot easily come out. So we say it is on drain, okay? And we also talked about if it is the drain, for example, that is coarse grain soils, then the strength is controlled by the friction angle, okay? That is the internal friction between the particles. But if it is the on-drain, for example, clay and silt, then the strength is dependent on the on-drain shear strength. That is the SU parameter, okay? And we also gave a brief introduction about the Moore-Coulomb failure criteria. We say on-drain shear strength is C plus sigma tan 5, right? So if it is on drain, the shear force is controlled by this, because the C will be SU, right? But if it is drain, then this value is mostly 0, so it is controlled by the friction angle. Okay, so if you get a good understanding of what is drain and on drain, it will make a lot of things easier for you in the future. But if you still confuse these two, then it will be a little bit problematic for you. The concept is quite straightforward and simple. So you try to just visualize it and make sure that some of these key ideas stick to you. Because these are some of the things that even when you go out to work, you will use them, right? Most of the calculations you do and all that, nowadays we have computers. We just input the parameters in the computers to do the calculation. But how do you ensure that what you are doing is right or wrong? You need to know what you are doing. Am I doing on-drain analysis? Am I doing drain analysis? Okay? So whilst in Taiwan, if you guys will have the opportunity maybe to do an internship, it's also a good learning curve. You can experience some of this. Because sometimes when the parameters are given to you in the book, it's too straightforward. But when you are working with a company or you go outside to get experience, you know how to organize the data yourself. Or most of the data is not straightforward. They will probably not give you like 5 other days. You might have the N, the SPDN value is this. So you need to go back, look at the other formulations, then you drive this friction angle by yourself, or maybe the SU value by yourself. So if you guys have the opportunity, you can think about doing an internship while you're here. It will give you a lot more opportunity to learn. I know like some of the students, the foreign students in the past, talk to some of the professors and the professors help them to talk to some of the people in the industry and then they can get an internship. Because if you, to be honest, in Taiwan, the one problem is that if you don't know people, it's kind of hard to get a job as a foreigner. So if you want to do internship or something like that, it's best you try to talk to a professor and then he can talk to the companies. Most of the companies, they'll listen to the professors. So if the professor recommends you to them, you'll most likely have a chance to go there. Okay? Okay, so moving on, we talked about the at rest lateral pressure coefficient, that is the K0. And then why is this important? Okay, so typically when we are doing analysis, we will evaluate the overburden pressure, okay? So for example, this is the soil, and here to here is the height, okay, of our soil layer. And then the unit weight of this soil is gamma, right? If we want to measure the overburden pressure at this point, it's gonna be what? This will be sigma V, right? Because it's vertical, we can calculate. So we will say what? Gamma, this unit weight multiplied by Z, okay? But how do we calculate the horizontal stress that is acting along here? Because if we are going to design a foundation or we are designing an excavation, the horizontal force that is acting on our structure is also very, very important. Actually, most of our calculation is with regards to the horizontal component of the force. Okay, so we can calculate this horizontal force from the vertical component by just using the K0 coefficient. That is the lateral at pressure coefficient. K naught sigma V. Okay. So here we have some equations that can be used to determine the K0 value. Okay. So this K0 is dependent on what? The friction angle. So you can see the friction angle is very, very important. It's a very important parameter. So you can imagine how bad your design will be if you get the wrong friction angle value, because almost everything you are doing relates to it, especially when you are dealing with sandy or soils that are like coarse grain. Okay, so this is our K0, and for OCR play we will include this time. Okay, the OCR. It also depends on the OCR ratio. So you have two different, either this or this, and all of these are okay. It depends on which one you want to use. So here you can see the same thing. They do a lot of experiments. So this is for cohesive soils like clay and silt. They have cohesion. Okay? So this represents the triangle. So you have a lot of them here. And then this one represents the cohesionless soils, like sandy soil. Okay? So they plot all of this and then they try to draw some line of best fit. Okay? And the line of best fit is what gives this equation. And then this other study came with this other representation. Okay? They used the horizontal stress index to determine the at-rest earth pressure. That is the K0 value. Okay, so typically for any of these problems, you will have a lot of tools that you can use. It's all about you knowing which tool is most suitable for the problem I'm trying to solve. Okay? You have to like pick and choose which one is the most suitable one for the problem you have at hand. It's the easy one. Okay. 来记有开吗？还是没有？
不知道，
会不会很热？
蛮热。
还是就这样？太热了。Okay, so typically we will use these values also a lot. Apart from the phi, the SU value, we will also, for foundation design, you will also use a lot of these K0 horizontal. Okay? Okay, so apart from our soil strength parameters, right? Another thing that is very important is the design load. Okay, if you're going to design the foundation, okay, you want to make sure, okay, I know the strength of my soil. Okay, I know the type of foundation it can hold, but also you need to know like how much load is your foundation going to sustain, right? If I'm going to build a 2-story building and a 5-story building, I should not expect to have the same type of foundation for the two products because they are going to support different types of loading. Okay, so it is very important for you to know what type of load your foundation will be subjected to. Okay, so here it says there are different types of sources of loading for our foundation. Okay, so the number one is the dead load. Okay, that's the load due to the self-weight of the structure. Okay, you build your foundation, and then now we build the structure on top of the foundation. This structure is called what? It's a dead load. It's fixed. It's not moving. It's not going to change. It's going to be permanently going to be on the foundation. The foundation needs to support this force forever. Okay, so this is called the dead load. It's not moving. It's permanent, attached to the structure. And then we also have the live load. Okay, the weight of the people and objects that occupy the structure, but are not permanently attached to it. Okay, for example, we are in this IB building. The foundation needs to support the whole entire structure, but during the day we have a lot of students. We all come here to take classes, so we also add to the load, right? But at the end of our classes, we leave. So we are live loads. We come and go. We are not permanently attached to this structure, okay? And then we might also experience other type of loads. For example, the water, earth pressure. Okay, water maybe in case of a rainfall or some unforeseen circumstances, wind. Like recently there was a typhoon in one of Southeast Asian countries, so you also have to take all those things into consideration. And then in countries where there are snow, because that will also add some sort of loading to your structure. So all these are very, very important. And then the seismic loads. In Taiwan, this is actually very important because every year you have so many earthquakes, especially this year, it was a little too much. It's like every time it happens, it's quite scary. Do you guys have any earthquake back home? No? Okay. So the first one must have been quite scary. It's the same for everyone. No one gets used to it. Okay. So here it says design load. For the purpose of design loads are calculated as specified in the application code. Okay. So when you design a structure or a foundation, you have to follow a design code. They will give recommendations. So it's not just like you rely on your intuition or your feeling to design. You have to use a design code. And most of the time, every country or every region will have a design code. Okay, because the situation in every part of the world is quite different. So each country or each area or each region might come up with their own design code that you can follow when you do your design. And why is it important? If you design something, you follow the design code. If something happens, it's not my fault. I follow the design code. You are safe. If you don't follow the design code, something happens, then you have to be held responsible. Okay? So whatever happens, you just make sure you follow the design code. So, and then they also will consider the load combination. So, for example, okay, earthquake, rainfall, the life load, the dead load, all need to be considered when we are designing the structure and the foundation. Okay, so here it says that all these type of loadings need to be considered. But if you are designing your structures in places unlike Taiwan, then it's a lot easier because you don't have a lot of seismic activities. But the ground condition, like in Taiwan, is also not that good. So if you get a chance to work here, just try it. Even for 3 months, you will learn a lot. Okay, so moving on, we will just quickly introduce some of the foundation design methods that are widely used. So we have 3 here that we will introduce. We have the working stress design, the ultimate strength design, and the limit states design. So we will go into each of these one by one. Okay, so it says the working stress design method, also called the allowable stress design method. The basic design inequality is what? The design load should be less than or equal to the allowable load. What is the allowable load? That is the maximum load that you want to accept on the foundation, right? So the design load that you get should be less than or equal to this. Okay, if it is less than or equal to this, then it means what? It's safe. But if it is more than then that leads what? On safety, right? So for example, here I say Q is the design load, working load or service load, and QA is the allowable load. Okay, but how do we get the Q allowable? Most of the time, the allowable will depend on what? Q allowable is equal to QU all over the factor of safety. Okay. So what is the QU? That is the ultimate load, the load at which this structure will fail. Okay. We know, okay, if that, for example, is 1,500. But we are dealing with soil. There are so many uncertainties. Okay? I know if I put a maximum load of 500 or 1,500 on this, it will fail. When I'm doing the design, do you think it's a good idea for me to set that value to 1,500? No, because there are so many uncertainties. So we will divide this ultimate value by the factor of safety. Okay? How safe do we want this structure to be? So you might have 1.5, you might have 2, you might have 3. That also depends on the design code. So for different types of structures or for different types of problems, they will give a range for the factor of safety. Okay, so you can use the FS value. So to get the allowable, you just reduce the ultimate by the factor of safety. So this QA here is just this Q ultimate divided by the factor of safety. In this case, the factor of safety is 3. Okay, so for the working stress design method, this is the whole concept. That's the whole concept, okay? The design load should be less than or equal to the allowable load. That's all it takes into consideration. So every calculation you do, you have to make sure that the design loading is less than or equal to the allowable loading. Okay, so here it just describes in detail like how do we get the Q allowable, just the Q ultimate divided by the factor of safety, and then we get the allowable, okay? Normal, that is the long-term condition, the load contained condition and the short-term. Okay, so usually also when we do analysis, we will also consider the long-term and the short-term condition, because the soil sometimes also will behave differently on the long and the short-term condition. When you just put the loading onto it, for example, when we are talking about clay, we might do the on drain analysis for short term, but in the long term you might consider consolidation, right? Because the loading is on it. Over time, it might cause the water pressure to dissipate over time, but that takes a lot of time. It doesn't happen immediately, but it takes a lot of time. So that's why sometimes we consider the long-term load condition and the short-term in a load condition. So in the short term, how do we expect the structure to behave? What is the soil condition? And in the long term, what is the soil condition? And how do we expect the structure to behave? So all these things are things that you take into consideration when you do the design. I think you will have a much better understanding of all of this in chapter 3 when you start doing some of the analysis for foundation design. Okay, and the next one we have the ultimate strength design. Okay, so this one depends on the strength, also called the load and resistance factor design. So we have a loading and then we assume that there should be resistance, okay? And the loading factor should not be more than the resistance, right? It can be less than or equal to the resistance. Okay, for example, if let's say we have a wall here, and then maybe the resistance from this end is 1,200. If the loading factor from this end is only 1,000, we can assume that this will still be stable because this is the one pushing, but this is the resistance. It is stopping this from moving this or causing this to get damaged, right? But if this becomes 10,000 and this is only 1,200, what happens? It cannot resist this force. If it cannot resist, what will happen? It needs to move. It needs to give way, which may cause our structure to have serious deformation or even damage, okay? So this concept is just based on that. The loading should be less than or equal to the resisting force that it is experiencing. Okay, so it says the word nominal or characteristics mean both the loads and the resistance are determined following certain guidelines. Okay, so in this case, just similar to earlier, most of what you do depend on the design code. Okay, so you will have a guideline. Okay, for example, they say, okay, if the friction angle is from this to this, then this particular value ranges from this to this. If this is this, the factor of safety needs to be 2, or it needs to be 1, or it needs to be 3. So you have a lot of guidelines that you need to follow. So almost everything you do here too is based on the design guidelines, not your own assumption. Okay. Okay, so here it says the working stress design versus the ultimate strength design. Both are force methods. They both rely on force. The absolute strength design, so you have the design load. The service load refers to the serviceability limit state. Uncertainties in loads and resistance are blended in the factor of safety, okay? So that's why whenever we do analysis, we have to include the factor of safety because we will have uncertainties in the loading and the resistance, okay? So you have to input the factor of safety, maybe 1.5, maybe 2, depending on your design. And the ultimate strength design, the factor load refer to the ultimate limit state. So uncertainties in load and resistance are reflected in the load and the resistance factors. So for either of these, both cases, they consider the factor of safety or the uncertainties, but in a different way. So we have this. For example, we have footing A. Then this is the ultimate loading for this footing. So what is the allowable when we do the design? Based on our guideline, okay, if the factor of safety is supposed to be 2, you can just divide the ultimate by this, and then you will get this. And then you can also know what is the displacement. And for footing B, which goes from here to here, we know this is the ultimate, we do the same thing. Okay, you divide it by a factor of safety, and then you can get the allowable load, and then you also know what is the displacement in this case. Okay, and this one, the limit state design method is actually newer. This one is a modern view of design. So it considers like various conditions or scenarios that you need to avoid. Okay, a limit state is a set of conditions to be avoided. The conditions that you want to avoid. So you have two basic limit states: the serviceability and the ultimate state. Okay, so for the serviceability state, what happened? Our system fails to perform its intended purpose. So, for example, we design a foundation. The foundation is there, but the design settlement during our design was we want a maximum settlement of 2 centimeters, let's assume. But after the design and everything, we start using the building, then we have a settlement of maybe 10 centimeters. The building is still there, nothing happens to it, but we have this amount of settlement. So we have this excessive foundation. We can still use it, but it doesn't fall within our design requirements. Okay, so it did not perform the intended purpose. For the ultimate limit state, what happened? When you reach the ultimate limit state, then that means you are at risk. Okay, the structure probably is destroyed, it got damaged. So it says, associated with the concept of danger or lack of safety. Okay, so it has serious structural damage, your structure might collapse. Okay, when we talk about the bearing failure, failure of your foundation, excessive foundation settlement, that you can no longer use the building. So when you reach this state, the structure is now unsafe. Okay, for this state, it fails to meet the limit, but it's not all that unsafe. It's still usable. For this state, it's just unsafe, not usable. Okay, it says the partial factors for load and material parameters are adopted for each limit state. Okay, when you are using the loading and the material parameters, we also have to use factors called the partial factors. That's like just the factor of safety. You have to assign a certain factor to each of the parameters, whether it be a load or material parameter, to account for the uncertainties. And then for the serviceability limit state, the load and the material factors are set to be 1. So for the serviceability, this one is just set to 1. Okay, so if we look here, it can actually give us a much better idea of this concept, the limit state design concept. So for example here, you have a very important structure. Here, you have an ordinary structure. And this represents an easily repairable structure. The structures that are not very important, but they're also very easy to repair. So here we have the magnitude of actions. That is how frequent this happens, or what impact we might observe, and what kind of damage are we willing to, or risk are we willing to take. For example, if it is high frequency, low impact. What does high frequency, low impact mean? High frequency means something that happens often, but the impact is not that high. For example, in Taiwan, we have a lot of earthquakes. Maybe earthquakes of magnitude 3 to 4, 5 are very, very common. Okay, you can say they are high frequent, and the impact mostly is quite low. It's like when you go beyond maybe 5, 6, 7, then the impact becomes much more obvious, right? But like 3, 4, the frequency is quite high. It happens like multiple times in the day that sometimes you don't even realize it. But the impact on our structures is low. So we want to make sure that our structures are all within the serviceability limit state. Okay, so the important structure, the ordinary structure, the easily repairable structure, they can all remain within this limit state in this type of condition. Okay? Because if something is high frequent and the impact is low and then your structure gets here, then something is kind of pretty wrong with your design, right? Because every time this happens, it happens very frequently. That means you have to repair. You have to do some work on your structure, which is not ideal. So we come here, medium frequent, medium impact. Happens more frequently, not all too often, but the impact is not really that high on the structure. So for this, the important and the ordinary structure, we want to make sure they are still within the serviceability limit state, like nothing really happens to them. We can just, after this event, we can still use them. Okay, we can still continue to use them. For the repairable limit state, we can just, okay, it's just the easily repairable structure, and this happens medium, so we just repair because it's easier to repair this structure. You don't want to invest too much money. For example, let's say an earthquake of maybe magnitude 6, you want to make sure that Taipei 101 is perfectly fine, right? Or our building here is perfectly fine. But if you are a farmer and then you are building like a house or a poultry at home, you probably really won't care much. Like if it gets damaged, you can easily just go again and build a smaller structure for your pigs or your hens, whatever. Okay, so in that type of scenario. And the low frequent, high impact, okay. Now, the low frequent, it happens rarely, right? In Taiwan, okay, let's say earthquake of magnitude 7, it's not that common, or even, let's say, close to 8. It's not that common, right? So the frequency is what? It's low, but the impact is high. Every time it happens, you have more damages, okay? You will experience a lot of damages. So in this case, we can accept that our important structures will need to be repaired after this type of event, okay? The important structures need to be repaired. But the ordinary structure and easily repairable structure, we are okay if they are in the ultimate limit state. That means they fail, okay? Or they are unsafe. Why is this important? Why don't we make sure that everything always remains here? We can do that too, right? We can design our structure such that everything always remains here. Even if it is high impact, low frequency, we can make sure that everything remains here. But instead of that, why do we accept this? Anyone have an idea? Why? Mm-hmm. Yes, it costs more money. It costs a lot of money to do the design for this because you have to be excessive in whatever you do, in all your design. So if you are the owner of the building, you are the one paying for the money. You want to spend as little money as possible. You don't want to spend a crazy amount of money, okay? So for example, sometimes if you are doing design, you say, okay, we want to design based on an earthquake of magnitude maybe 8.5. And then you go to the owner of the building and then you tell him, but maybe this happens only once in 100 years. If you are the owner of the building, what do you say? Oh, okay, it's okay, it will not happen in my lifetime. You will just believe that, right? This is, for you, it will be too crazy, right? 8.5 now. So, it's the same thing. Every time you take things to the extreme, it becomes more and more expensive. And that's always what the design engineers, like the problem design engineers will have with the construction companies or the owners of the building because they don't want to spend a lot of money. Like, right now I work for a consulting company and mostly that's usually the problem because the design company will design the structure and then they pass it to the owners of the project. And the owners of the project will be like, this is not reasonable, it's too much. So they will give it to the consulting company. You try to check and see, oh, is this design reasonable? What can they do to make it like less expensive? Because the owners of the building are always looking for a way to make their project less expensive. So that's why we have this kind of workflow. We can always use this, which is acceptable for most people. Okay, and it also relies on the design code, so you are not putting yourself at risk. Okay, so here it says the performance-based design specifications. The Railway Foundation Design Specification, Railway Technical Research Institute has moved towards the performance-based design. So in this design, both the force and the displacement are required to meet the requirements. Okay, so for this type of design, it's not only that you consider the force. You don't only consider that, oh, my structure should be able to withstand this force. But you also want to make sure that the displacement is within a reasonable range. Okay, So you can build a building, the building still stands there, it's fine, nothing happened to it, everything is okay, but the displacement is unreasonable. Your first floor become B1, nobody will accept that, right? It's still not ideal. Or you design a road, but it's full of bumps. Okay, so you have to consider that not only the force should be okay, but also the displacement needs to be fine. Okay, so it says the limit states general condition. We have the serviceability limit and the safety limit. And the earthquake condition, we have what? Repairability limit for residual displacement and safety limit. So if there's an earthquake condition, for the most time, we can accept repairability. That is to repair some of the structures. Okay, some damage might happen, so you might provide some support to your columns or do a minor repair work on your structure. So most of these concepts will be explained later in detail in chapter 3 once you start working on the foundation design proper or introducing like some of the different types of foundation design. Okay, I think we can quickly take a look here. This video is showing the SPTN done in the field. Okay, so they will usually have a lot of equipments. They bring in the equipments, then set it up. Okay. Okay, and then they will drill a hole in the ground to make sure it reaches a certain depth first. Okay, that's the tube. You put it in the borehole you just created, right? And they mark, because you have to make sure that it goes to a certain depth. You have to know the length that it passes through for each blow count. Okay, fix the head, and that right there, oh, this is the hammer, and then they will just drop it. You take it to a specific height, drop it on this, take it to a specific height, drop it on this, until it reaches the 15 centimeter mark. So you can see, okay, it's going up to that specific height. Take it up to the specific height, and then you release it. Okay, because you put the tube inside, so inside the tube you can also get some soil samples. But mostly these soil samples are just used for classification, to just give you an idea as to what is the soil profile at the site. Because you are using the hammer and then you are hitting it, bam, bam. So if the soil you get is highly disturbed, it's highly disturbed. So most of the time, the soil sample collected is just used for the classification. It's still the same thing. You type the tube and then drop the hammer. I think the concept is actually quite simple. You have a hammer, you have a steel tube, and then you drop the hammer onto it to penetrate into the soil. If the soil is very strong, for example, let's say we want to go through 15 centimeters of this soil layer, right? If the soil is very strong, we need to hit the tube more times for it to go through 15 centimeters. But if the soil is not strong enough, you need fewer falls of the hammer to go through this soil layer. So the concept is actually very, very simple and straightforward, but it can give you reasonable results for your analysis. Okay, so apart from this SPT, we also did the CPT. The concept, okay, this is the CPT. You can see here. So you have like a cone, and then you pushing it into the ground. Okay, so they have this, push it into the ground, and this is like a cone. So here we have the QT, that is the resistance at the tip. And then they have another instrument here that measures the U. The U is the pore water pressure at that specific location. And another parameter that you can calculate from the CPD is the FS. That is the friction between the sleeve and the soil. Okay, so you can see like from the CPT you can actually get more parameters. You can even get the pore water pressure. Okay, unlike the SPT. So the concept for the CPD is also similar. You can see soft clay, medium clay, and the bedrock. Okay. So here the QT is the tip resistance. That Fs is the friction between the sleeve and the cone, and then this is the pore water pressure. So you can see here, because this is soft clay, so the tip resistance will be what? Smaller, because it's softer. But when you get medium clay, it's stronger. So the tip resistance will be more. And then the bedrock, it increases even more. So for this CPT, when you just insert it into the ground, you can just record these values automatically. Okay, for the SPT, most of the time you count the number of blows that you are doing. But for the CPT, you have a computer that can automatically help you to record these values. And this is the same thing, the friction resistance. Because if this is soft clay, the resistance between the clay and the CPT will be smaller. You get to medium clay, the resistance will be high, and then in the bedrock it will be even much higher. And then the same, here also we can measure the pore water pressure. So you can see here the pore water pressure is much larger because it is the soft clay part. And then in the medium clay, pore water pressure is like small, okay? Because the particles are more tightly packed. I think I have a this one? Oh yeah. I think this shows the setup for the CPT. Okay, then just get the car, push it to the, okay, this is the, here, that's the computer that they use to just measure. Okay, so you just attach it and then you just go. You don't need to record it manually. Okay, take it to the right location. You anchor your machine and then prepare the CPD equipment. So this is the specification. You have different, this one is 10 centimeter cone and then the other one is the 15 centimeter cone. So you can choose either one. Okay, and then once it is being placed into the ground, then you can automatically record some of the readings. Okay, so it says, okay, for example, here we say the limitations of the CPD, no soil samples recovered. You can remember the SPT, the tube have a hole inside, right? And in the hole, you can get some of the soil samples. But for the CPD, you cannot get the soil samples. Can only exert a certain maximum amount of force, right? So if our soil is super hard or too strong, then the CPD might not be ideal because it cannot penetrate through the soil. okay, and not applicable to gravelly soil and hard rocks. Okay, if the soil is like gravel, then you cannot use it. But it is accurate, reliable, and then you can also use it to get the pore water pressure. You can use it to get the tip resistance, which you can use to determine the undrained shear, the SU undrained shear strength, and even correlate it to the friction angle. Okay, so that's all for chapter 2. If there are no questions, we can have a break now. Okay? Yes. Typically, yeah, you guys experience. Okay, so let's continue. And hopefully we can finish a little early. I'll just give a very quick introduction here to chapter 3, which is the shallow foundation. So for chapter 2, actually it was mostly talking about a lot of the concepts that we might need to use when we do foundation design in the preceding chapters. But sometimes it's kind of difficult to wrap your mind around all the concepts that have been discussed if we don't put them into use. So I think most of the things in chapter 2 will become more visual to you in chapter 3 once you start doing some of the designs and then you begin to use some of the parameters. Then like you get a real feeling of what the parameter or what we were talking about in chapter 2. Okay, so for chapter 3 it just talks about the shallow foundations. Okay, so when we talk about shallow foundations, these are foundations that are close to the surface. Okay, they are not that deep. So we have different types of foundations. We have the shallow foundations and the deep foundations. Okay, for this course, most of what you will do will just be on shallow foundations. Okay, so the definition of shallow foundations is actually quite straightforward, right? These are foundations that transfer the structural loads to the near surface soils. Okay, so why do we even need foundations? Because we want the foundation to transfer the structural load to the soil in such a way that the soil can sustain the loads, right? So if the load transferred by the foundation is just near the surface, then it's called a shallow foundation. Okay, so here we have different types of shallow foundations. We have the spread footings and also the mat foundation. Okay, so your typical spread footing is like this, right? You can just put it like this, but we will instead have something like this. Okay. So, do you have any idea why we will use something like this instead of this? Hmm? Yeah, it gives you more surface area because we are trying to transfer the loading from our structure to the soil. So when we do this, it gives us more surface area, right? And we say what? Right. So the larger the area, the more it can distribute the stress. But if this is like this, it can easily cause failure, right? Because the stress will be significantly higher. So that's the whole idea about spread footings. You just have a footing which will help you distribute the loading, okay? Or you can say, how about we just make it this big? That's okay too, but it's not economical, right? And then if you are designing a building, you also need space. So if your column is going to be that big, it just doesn't make sense. So the best thing you can do is this, right? Make sure this column is big enough, but once you get to the bottom of the foundation, you can spread the loading over a larger surface area. Okay, so this is the typical isolated footing. You just have one footing in place. Here we have what we call combined footing. So this is if the soil condition is actually very good. Okay, but if you feel like the soil condition is good but not as good as this one, or I need more footings, then you might need to combine some of your pile. Okay, the footings here, you have to combine them, put them together. So this is called the combined footing. And in some cases, you will have a wall. What does it mean? Okay, initially we will design like this. You put one footing here, one here, or maybe you put two together. But if you still feel like, okay, this design is not enough, you can just make this to be long enough, right? You just go all the way around the building. Okay, so this, instead of having only a footing like this way, it goes in. So you have like, this is a 3D representation. Okay, so it's much longer. For this one, maybe it's only like this big. Okay, it's here, like this. But in this case, this footing is actually very, very long. It's much longer. Okay, so this is called the continuous footing. Why? Because the length is proportionally longer than the width. Okay, so the length of the footing is much longer than the width. And in other cases, we might use the mat foundation. What do we mean mat foundation? It's just like the English word MAT, mat. Okay, you just spread it on the ground. So that means the whole area of the building becomes your foundation. Okay, so it's just like my piece of land that I want to build on, then I just spread on a mat onto it. So that means the whole surface area here is my foundation. Instead of just having this spread footing or this or this, this one also depends on specific conditions, because before you design the foundation, you need to know, okay, how much loading does the foundation need to take, right? Or what type of structure am I building? The more load the foundation need to take, the more footings you will need. But if you design the footings and you realize that, oh, the number of footings I need is too much, then you will just use a mat footing instead. So it's like a mat foundation instead, because it's more reasonable. I think in the next slide we will see, it will give a much better. Okay, so it says a spread footing is an enlargement at the bottom of a column. Okay, so this is our column from the building, and the spread footing is just the enlargement at the bottom of the column, or the bearing wall that spreads the structural load over a sufficiently large soil area. Okay, as I mentioned earlier, we spread this to make sure that the loading is distributed to a sufficiently large area of soil. Okay, and it says the spread footings are the most common type of foundations because of their low cost and ease of construction. So they are typically used in construction projects, especially if the buildings are not very tall, or you don't need a lot of, or the soil condition is good enough, then we will use the spread footing because they are cheap. Okay, they are often used in small to medium sized structures on sites with moderate to good soil condition. So using the spread footing also depends on the soil condition on the site. Okay, because you are transferring the load from the building to the soil, right? So what the soil need to be able to sustain the loading. So that's why the soil condition needs to be good. If the soil condition is not good, then you cannot use a spread footing. You might have to think of other different alternatives. Okay, so this one is the mat foundation. So the whole floor area now is a foundation. Okay, so it says for weaker and compressible soils, it is more efficient to use a mat foundation. Okay, when the size of spread footings cover more than half of the entire building footprint. Okay, so if this is our building footprint and we want to use a spread footing, we realize, okay, we can use 1, 2, 3, 4, and maybe one in the middle, 5. Okay, it's good enough. This foundation can support our structure, then okay, it's reasonable, we can still use spread footings. But if in a scenario we realize, oh, this is not enough, we might need to add 6, 7, 8, 9, or maybe even more in the middle, it just becomes unrealistic. Okay, it's just too much. So we will just use the mat foundation instead. So we just use the whole floor area to spread, to be at the foundation area, right? So it says, when the size of the spread footing cover more than half of the building footprint. If it is more than half, then we will just use the mat foundation. Or if the soil is weak. And it's also compressible. It is easy to compress. Because if the soil is easy to compress, what happens? If you apply the loading, it will settle, right? And if that happens, this spread footing and this spread footing and this spread footing are independent of each other. So you will have uneven settlement. The rate at which this footing will settle and the rate at which this will settle and the rate at which this will settle might not be exactly the same. So you will have problems. But if you use a mat foundation, then the settlement will be more even if you have a settlement. Okay, so that's also another scenario. Okay, so it says a mat foundation, also known as a raft foundation, is a very light spread footing that supports most of the structure. So it's just like a spread footing, but in this case, it is just flat all over the whole building area, just like spread like a mat. It says the large size of the footing base can help reduce the contact pressure between the bottom of the footing and the soil. So, exactly, because we have here, this is our area, right? If the spread footing is here, then that means most of the loading will be supported by this end. If it is here, most of it will be supported by here. If it is here, most of it will be supported by here. But if we use the mat foundation, this is our building structure, right? That means the whole entire loading from the structure will be distributed throughout, okay, over the whole area. Okay, so here we have the components of solar foundation design. So what are the things that we need to check if we are going to design our solar foundation? Okay, so number one is the capacity issues. That's 1 and 2. So you need to check for the vertical bearing capacity. So you need to make sure that the loading from the structure can be sustained. Okay, can be sustained by the soil. So you say the bearing, Q bearing, the bearing load should be less than or equal to the allowable Q. Okay, and then we already mentioned that the allowable Q is mostly, or is always the ultimate, okay, the minimum force at which the structure will fail divided by the factor of safety. Okay, the factor of safety is determined based on specifications or design guidelines. Okay, and then we will also do an eccentricity check. Okay, in the next slide, in the coming slide, we'll see what eccentricity is about. And then also settlement. So for the soil to be able to bear the loading is one thing, but also another very critical component is settlement. We want to make sure that the settlement is within reasonable rate. So the SF, the settlement of the foundation, should be less than or equal to the allowable settlement. Then you will have the structural design of the foundation slab. Okay, you integrate the structural components. Okay, so here we will just quickly describe what is the vertical bearing capacity. Okay, so the vertical bearing capacity is just you have the soil layer, and then maybe you have your building here, right? And then you will experience some sort of a vertical loading, right? So we want to make sure that the vertical load can be sustained by the foundation and the ground underneath, right? So the first thing is the ultimate bearing capacity. It says the bearing pressure under which the soil reaches failure or produces excessive settlement. Okay, so it depends on two things. The settlement is unreasonable or the soil fails. Okay, in some cases maybe the soil does not fail, but the settlement is unreasonable. So both scenarios are not ideal. So we have the QU is, I think should be Q. Oh yeah, the Q. The force by unit area. This is like measured in stress divided by the Q. That is the loading divided by the area. Okay, so this is measured in stress, like stress, and this is the loading, and this is the area. Okay, so it's more like this, the distribution. So what you have here will be Q, but this one will be small q, which is the loading divided by the area here. That is the distribution. And then we have three zones. When we talk about vertical loading, we have the failure mechanism of a footing on the vertical load. Okay, so when you apply a loading, three things happen. You apply a loading here, what happens? The soil underneath will, first and foremost, will what? Go down, because this will push this down. It's a loading. If this pushes this down, what happens? This will most likely start moving this way. If this moves this way, what happens? If it has nowhere else to go, that means the soil here needs to go up. Okay, so usually this is how the failure mechanism is described. You apply a load in here, the soil here moves down. When it moves down, it doesn't have anywhere else to go. What happens? It pushes the soils on the side. This one pushes this one on the side. Where else will they go? It's easier for them to go up than to go down. So they will push up because the resistance down is more. Okay, so here we have some images and it says the bearing failure modes. So when we talk about the vertical bearing capacity, we have different types of failure modes. We have the general, we have the local, and the punching failure. Okay, where do we typically experience the general shear failure? So general is mean like the overall structure fails. Okay, and the local is maybe just a certain area fails, and the punching is just your footing just goes straight into the soil. It just punches the soil and goes in straight. So for the general, we usually experience it in dense sand and stiff clay. And why is that the case? If the sand is very dense, or it is clay that is stiff, if you push this down, it doesn't have anywhere to go because there is not much space within the particles. It is already very dense. There's not much space. So what happens? You push this down, it obviously have to push this one this way and this one that way. And if this moves this way, this moves that way, then what happens? They must push it up. So you will experience failure here and failure there. So it is called general shear failure. And it happens in dense sand and then stiff clay because of the nature of the material. Okay? And this is called the local shear failure. So general is the overall area of the experience failure, and the local is just some area. This medium dense sand, okay, which is quite reasonable because you push it down. It's not very dense, but also it's not too loose. So some of the particles will move in to fill the spaces between the soil. But once that is completed, what happens? They need to push this out, and then move up, right? But not every particle that moves down will be pushed up. Why? Because there are some spaces between the soil that needs to be filled first. Once the spaces are filled, then it will move up. So you can see the failure here is not as evident as you see here. When it pushes this up, it's bigger. Here also the same, it's bigger. But here is, you will observe just very little ground movement here. The same thing happens here. And the punching shear failure happens in what? Loose sand. You can imagine why. Why will, if this is loose sand and then you put your column here, why will it just go down? Exactly, because there are spaces between the particles. So what happens first? They will fill in those spaces. The spaces are large enough for all of them to fit there, so they don't need to push anyone out, okay, or up. So that's why we will experience this type of failure in the loose soils. Okay, so by seeing that diagram, you should know, okay, the soil I'm dealing with is dense or stiff clay, or like that, you know, okay, that should be a medium dense. Or if you experience punch, then you're like, okay, that should be loose soil. Okay, and here we have the general shear failure. It says it occurs for a foundation resting on the surface of a dense sand or stiff cohesive soil. Okay, we already talked about that. If a load is gradually applied, the foundation settlement will increase. Yeah, so which is reasonable. The more load you apply, the more the settlement will increase, right? Failure in the soil supporting the foundation takes place at a certain point when the bearing pressure reaches a certain value called the ultimate bearing capacity. So the ultimate bearing capacity is the maximum load that we expect our foundation to be able to sustain. So once you go beyond that, what happens? You have failure. Okay, so that's the ultimate. So it says after the ultimate point, the footing can no longer sustain more pressure. Okay, if you pass the ultimate, it can only fail. It can't handle it anymore. Okay, general shear failure in terms used for the sudden failure in soil. The three mobilized zones, so we already talked about this: zone 1, zone 2, and zone 3. Down, out, up. Okay, and here we have a diagram for the general shear failure. So this is the settlement you will experience, and this is the bearing pressure, right? You apply the loading, the bearing pressure keeps increasing, you have more settlement. You have more settlement, then you reach here, the ultimate point. Now the soil has failed. What happened? This gets even much larger. You have a very large settlement, even though the Q is not as high, but this becomes unrealistically larger. Okay, but you can also see that the load needed for the general shear failure is actually larger than the local shear and the punching, right? Because this affects a larger area. This one is a smaller area, but this one is even much smaller. Okay, so here is the same thing. The local shear failure occurs for foundations resting on sand or clay soils of medium compaction. Okay? So you are dealing with sand or clay, and the compaction is medium, right? So we will experience the local shear failure, which is this type of failure, okay? And then increasing the load will also increase the settlement. And the failure zone in the soil will gradually extend outward from the foundation, okay? So you will see the failure zone come out gradually, but it's not as evident as in the general shear failure problem, right? So it's much different. So you can see here, okay, you reach QI, and but this one, this is the Q ultimate. That's the local shear failure, okay? The Q ultimate is here. By the time you reach the Q ultimate, the settlement is even much larger, right? Look at this one, the general shear failure, the Q ultimate is here, much larger, but the settlement is still a lot smaller than this one. By the time you reach Q ultimate, the settlement is already pretty large. Okay, so here it says when zone 1 and 2 are mobilized. So this is zone 1, this is zone 2, right? When zone 1 and 2 are mobilized, the bearing pressure reaches QY. This is mobilized, then you have this point called QY. Beyond this point, the settlement significantly increases. So it says, you see it like this, the Q bearing increases, but the settlement was not that much. But you can see that Q bearing increment from here to here, it's not that much. But the settlement increased significantly from this to this. That's a very huge margin. Okay? So it's a considerable movement is required for the failure surface in the soil to extend to the ground surface. Okay? So because this is the ground surface, right? This soil is not tightly packed together. If this moves here, and then it pushes this here, you need a lot of movement for this to move up. You need, unlike the general shear failure, the soil is very dense. This moves here, and it comes here. You don't need a lot of movement for this to move up. Why? Because there is no space for them to go. They can only go up. But in this case, if it comes here, it comes here. For it to come up, it still needs a lot of movement for that to happen. Okay? And it says the bearing capacity, that's here. Where that happens is called the ultimate bearing capacity. Okay? So we can also see it here. The ultimate bearing capacity for this one and this one. That's the general shear failure, and this is the local shear failure. And finally, the final one we will see is the punching shear failure. Okay, for the punching, it says it occurs for foundations that is supported by the fairly loose soil. So the foundation is placed in a fairly loose soil. Okay, the failure surface in the soil does not extend to the ground surface. Only zone 1 and or 2 can be. So in this case, you experience settlement here only in zone 1. You might have in zone 2. It might be, but not necessarily. The bearing pressure settlement plot is similar to that of the local shear failure, however, it is softer. Okay? So you can see it doesn't take much bearing pressure compared to the local shear failure for you to have punching failure, because you are dealing with much softer or loose soil. And then it's the same thing. Once it reaches this yield point, then it significantly, the settlement just significantly increases. So for both these, that is the punching shear failure, the local shear failure, and the general shear failure, is beyond the ultimate bearing capacity. The pressure settlement plot will be steep and linear. Okay? So once you reach the ultimate, right? The settlement will be very steep and linear. You don't need to even increase this anymore, but you will experience a huge amount of settlement. Why? Because the soil has already failed. It cannot sustain the pressure anymore. It cannot help. Okay, so once you reach the ultimate point, it fails. So that's why whenever we do design, we have the Q. Instead of using that actual Q, we will use what? Q allowable, and then you have Q divided by the factor of safety, just to be safe. Just to be safe. Because if you reach that ultimate point, there's no going back. It's just your structure is going to fail. So that's why we usually rely on the QA, the allowable component, so that even if we reach this point, our structure might still be safe. Okay, so do you have any questions about the failure mechanisms, the general, the local, and the punching? No? Okay, I think then if no questions, we can stop here for today, and then next week Professor Lee will be here. He can continue with the actual application of the various equations to solve the foundation design problems. Okay. Thank you all.
Ini kan masalahnya dia.